All right, so we're very happy to have for today's Institute for Quantum Studies seminar, Dr. Subhrajit Modak is coming to us from India. And so he'll be talking to us about some of his recent work that he's been researching with his collaborators there in India. He is a postdoc now at the Indian Institute for Science and Technology in Modi. And before that, he served as a visiting postdoctoral fellow at the Weizmann Institute of Science in Israel, as well as in Chennai, India. And his PhD is from Calcutta. And so we're very happy to have you joining us today. And so I'll turn the time over to you, and we'll look forward to hearing what you have to say.
Thank you, Professor Jordan, for this opportunity. And should I now share my screen?
Please.
Yeah. Yeah. So the screen is quite visible, right? Just want to know whether my screen is visible or not.
Yeah, everything looks great.
Everything. Yeah. Okay. So morning, everyone. So as you can see, the title of my talk has a little change. So the title is like saturating quantum advantages in post-selected metrology with positive Kirkwood-Dirac quasi-probability distribution. So you will get to know as I'm progressing why I'm emphasizing more on positive Kirkwood-Dirac distribution, right? So I am Subhrajit Modak. So I'm a postdoc here at Indian Institute of Science, Education and Research. This is the northern part of India. So this is Mohali. Okay. So this is the outline of my talk. So I have designed my talk in a 3 sections, right? I will first introduce what the Kirkwood-Dirac quasi-probability distributions are. So then I will move on to quantum metrology. And at the very end, I will discuss about what post-selected quantum metrology exactly is, what are the quantum advantages, how to bound those advantages, and to quantify what are the resource for these advantages. Then I shall move on to conclusion. Okay. So, yeah. So this is, as you know, the 2 kinds of quasi-probability distribution coming from the phase-phase distribution. These are very well-known quasi-probability distribution. The first one is the Wigner distribution, and the second one is the Glauber-Sudarshan P distribution. Here, this alpha are the coherent state space. So, apart this quasi-probability distribution, around that time, Kirkwood also introduced a quasi-probability distribution, which is not as much known as these 2 are. So, yeah. So this is the paper of Kirkwood-Dirac quasi-probability distribution. If anyone wants to know something better, so you can go get to see the paper. And further, when Kirkwood introduced this direct probability, Kirkwood introduced this quasi-probability distribution, this got further contributed by Dirac. So this is why the name is after Kirkwood and Dirac. So now I will show you what is this Kirkwood-Dirac probability distribution exactly is. Right. So in this protocol, I will mostly be telling about discrete setting, the discrete observables. So consider an arbitrary state, this is rho, and 2 non-commuting observables. These 2 non-commuting observables are A and B. So this A and B are non-commuting, right? So, and you can span your A and you can span your B in terms of these. So now what Kirkwood did, Kirkwood put a more restriction onto this. Not only this A and B are non-commuting, but their individual projectors are non-commuting also for every M and N. Right. So now, keeping this condition attached, what he showed that any state, this row, the first box you can check, that any state can be expressed as this P, M, Bn, and this outer product of Bn and M. So, where the denominator is just a inner product of M and Bn. So, in literature, this term, this outer product of Bn and M, is known to be like conditional state that you can achieve after successive projective measurements. So the form of this Kirkwood-Dirac quasi-probability distribution is like trace over rho AM and BM. This AM and BM are mutually non-compatible. Okay, and the interesting thing is that this Kirkwood-Dirac quasi-probability distribution can have complex values, right? Can have complex values, and not only this, this Kirkwood-Dirac quasi-probability distribution are informationally complete. So what does that mean? If you want to extract any information about the state, this probability distribution would be sufficient to have the description, right?
So can I interrupt you for just a second?
Yeah,
there
sure.
is a request for you to turn on your video and to speak a little bit more slowly. Can you do that?
Okay, yeah, sure. So my video is
Thank
on, right?
you. Yeah, it's fine. The slides are fine.
Right. Should I talk more slow, right? Yeah. So the Kirkwood-Dirac distribution fully express the state. Means what does this mean? This is actually informationally complete. So I will show you later how these are informationally complete. So this distribution that is in the green box, it seems like a complex joint probability distribution. So if you calculate the marginals, these are exactly like trace rho over Bn and trace rho over Am, right? So now I will show you how this Kirkwood-Dirac quasi-probability distribution can be simulated in terms of successive projective measurements. Yeah. So far, if you have any question, please ask me and interrupt me at any point of my talk. Okay. So far actually what I considered only the individual projectors of the observables are non-commuting, and this express the density matrix in terms of this Kirkwood quasi-probability distribution. And in the green box, you can see what is the form of this Kirkwood quasi-probability distribution is. Okay, so yeah. So this is actually just the slightest description how this Kirkwood-Dirac quasi-probability distribution can be realized with successive projective measurements, right? So now you can see what the successive projective measurements are. The state of the measurement will depend on whether we perform a measurement of the complete observable A or just one projector AM. For the time being, I'm considering only a particular projector, that is AM. For a non-selective projective measurement of the Ludus type of a particular projector AM, the post-measurement state becomes this, rho prime. So AM rho AM is a selective part, and the rest of the part is non-selective. This is why I'm calling it as a non-selective state. Okay. So now after this, so the selective post-measurement state, what would be the selective post-measurement state after applying the projector AM? So rho S prime is the post-measurement state after the rho is being measured at M. So A projective measurement of the observable, B is made on the system after a selective measurement of AM. So what are we doing? We are doing nothing, just we are first measuring AM, then we are checking what is the post-measurement state is. Then after having the post-measurement state, I'm applying another measurement, which is BN, and this AM and BN are not mutually compatible. This is why you can't shift the ordering. So after having all this, the probability of obtaining the eigenvalue Bn conditioned on AM is like this. So this is form of the like joint probability distribution, right? So now after this, so this formula, this joint probability of obtaining successively the eigenvalues AM and Bn, this formula was introduced by Wigner for successive measurement for observables with non-degenerate spectra. So now you can see if you check the marginals. So the marginals are not like the Kirkwood-Dirac quasi-probability distributions marginal, right? The first marginal is a marginal with respect to the pre-measurement state, which is rho, and the marginal which you are getting after that, it's a marginal with respect to the post-measurement state, rho prime, right? So now you can see this Wigner formula is not informationally complete. So now when I was saying that the Kirkwood distribution was informationally complete and it can be realized in terms of successive projective measurement, So you can write the Kirkwood-Dirac quasi-probability distribution in terms of this Wigner formula. In addition to this, you need some extra term that can access those missing informations. So this is why actually I was just showing these slides just to have a flavor how this Kirkwood-Dirac quasi-probability distribution are related with successive projective measurements. Now I will get into the main part of my talk. Yeah. So now, as you can see, the first part is the Kirkwood-Dirac quasi-probability distribution, as I have written. So now this part can be expressed as a combination of probabilities in successive projective measurements. So now the left-hand part is the Kirkwood-Dirac quasi-probability distribution. The first part in the right-hand side, as you can see, this is the Wigner formula. This is completely real. And the last part, which is imaginary. Now, if you diagnose this formula little carefully, you can see that the trace part, how the trace part is actually taken. So the trace part is actually taken the average of Bn with respect to rho, the difference of the average of Bn with respect to rho m prime, means you are having the information after a measurement am has already happened. So you are taking the expectation value of Bn with respect to the pre-measurement state and with respect to the post-measurement state. So this is how you can compose the total information in the Kirkwood-Dirac quasi-probability distribution with a Wigner distribution, with a Wigner formula and some additional part. So this is like this. So now this is very obvious that I have shown you earlier how this rho m prime is and what is this Bn pi by 2 is. Bn pi by 2 is just a notion. This is nothing more than this. It's a projector. Okay, it's a rotated projector. So now if you can check, you can see, sorry. So now if you can check, you can see this quasi-probability distribution, the Kirkwood quasi-probability distribution can be written in terms of weak values. So from this condition, it is also obvious that this quasi-probability distribution can have complex entries. So now the question arises, how to define the notion of non-classicality? Initially, what the literature had suggested that it is sufficient to declare the non-classicality in a probability distribution if you are having the real part of your probability distribution is less than 0. But in our case, I will show you and you will get to see as the talk progresses. So this condition is not as much strict as the condition written at the last line. So what I want to convey in terms of deciding non-classicality, this condition is not sufficient. So if you if you have this condition in terms of this, as it is written in the last line, this trace over rho am dn is not equals to the Wigner formula, then probably it is easy to refer whether there is non-classicality or there is not. So far, if you have any question, please ask me, because all these are prerequisite that is needed to exploit the last part of my talk. So I will use this Kirkwood-Dirac quasi-probability distribution in the further slides. So these are all notations and these are all representations. So nothing more than this. Yeah. So if there is no question, I'm getting into the next part of my talk. So the next part will be quantum metrology. So what this quantum metrology is. So the first part is not separated from this second part of the talk. So I will introduce the first part of my talk at the very last stage. Okay, so when I will be saying what the post-selected quantum metrology is and what are the quantum advantages. So what is actually quantum metrology? What is actually metrology? Metrology is actually a theory of measurement. This offers you to have optimized protocols through which you can get the estimation error of your estimator to be minimum, right? So how these metrology schemes operate? So suppose you are making a system, this is rho, is a density matrix, and you let it pass through an encoding procedure, right? So the encoding procedure we are addressing, that is purely unitary encoding, and the system we are referring here actually the PO system, PO state. So after having the interaction with your encoding block, your state has got some information about the parameter which you are going to measure, right? So see the orange block, the information of theta is encoded, right? So after having the states collected, you need to have measurements. So after the measurements, you will have all the data. So when you are stacking the data, what classical Kramer bound says, so you can't minimize your estimation error, right? Your estimation error, which is inversely proportional to 1 by Fisher information. Look, the classical Kramer bound gives you the lower bound, right? So this is the minimum amount of error you have to compromise with. So how this classical Fisher information is calculated, this is just a straightforward formula. I am not going into the detail. So now I will come into the case, what is the quantum metrology? So when the quantum metrology, I am talking about quantum metrology, how this is different from classical metrology. In case of classical sense, you can have your initial state which are non-correlated. And in case of quantum metrology, you can have your states which are correlated, which may be entangled and which may have share some other correlations. So now actually it is also going through some encoding procedure. After that, you are collecting the states, and after that you are measuring all the things. So this is called the quantum Kramer bound when the variation is inversely proportional to the quantum Fisher information. So now how quantum Fisher information is different from the classical Fisher information? Quantum Fisher information is the maximized or the optimized over all POVM. This E hat epsilon are the different E hat corresponding to different outcomes, right? So this is optimized and optimization for the maximization, right? So this is how the quantum Fisher information is different from the classical Fisher information. So if you write the initial state, the initial pure state as psi I, and if you are having your unitary encoding is like exponential minus I theta A is the generator of your coding. So you can write simply the quantum Fisher information like this, right? So now if you replace your U theta, so the notion of IQ theta would be like 4 of the variance of A with respect to the initial state, right? So now you can see, in spite of having optimization at the output, in case of quantum metrology, you will have the access to optimize the input state also, right? Because you can manipulate the correlation, you can have maximally entangled state, you can have minimally entangled state, whatever optimization you can afford for your protocol, you can have it. So there is another set of optimization that can be run over input state. So if you run the optimization again for the input state, it would be like delta small a square. What is the delta small? Delta small a is nothing but your encoding generator eigenvalue difference, the maximum eigenvalue and the minimum eigenvalue difference square. So this is the maximum Fisher information you can have from a particular protocol. This is the bound, right? So this is the bound. So now let's see the next part of my talk. This is postulated quantum metrology. So we are aiming to violate the bound, whether it is possible, and if it is possible, how it can be possible, right? So yeah, let me go to the next part of my slide, right? So this is the apparatus for the postulated quantum metrology. This is the same apparatus. So I am adding just a single component. It's like a post selection. So this protocol and the protocol that I have shown previously is more or less same apart from this post selection block. So the preparation is like an initial preparation is a pure state. Then the encoding procedure, you are collecting the psi theta state. After having the states, after having the encoded states, you are passing it through a post-selection block, right? So you are collecting data from the successful post-selection and you are discarding the data from the failed post-selection. After having the states with successful post-selection, you are measuring all the things that you want to calculate for your protocol, okay? So now you can see the post-selection. Now here, notice that your post-selection has to be at least minimum as second rank projector, right? So if you are having only a single projector, that would not be a post-selection. That is just a measurement. Okay, so you need to have at least a 2-rank projector in the post-selection block, this A prime, right? So after having the post-selection, the psi theta PS is a post-selection state, and this is the post-selection probability. And similarly, as the calculation as I have shown, so if you just put the things, you will have the post-selected quantum Fisher information in terms of this, right? So this psi theta dot PS at the post-selection state, everything is noted there. So now you can see the Fisher information cannot be a negative value, right? So in order to have something physical, so the first term has to be greater than the second term. So this is the post-selected quantum Fisher information. So now what I was talking about quantum advantage. So what the quantum advantage actually means. So quantum advantage, previously what I have shown you, at max, the error can hit delta A square, right? So you can never have a situation where you can supersede that limit. So quantum advantage, I'm calling quantum advantage when your IQ theta psi theta PS, the post-selected quantum information can have, can supersede that fundamental bound, this delta A square, right? So this is somewhat the experimental, this is somewhat the theoretical setup that actually shown by Shetlight group. So that got published in Nature Communication. So now we are arguing if you are having some situation that your post-selected quantum Fisher information can get rise to infinity, what about the post-selection probability? What about the probability that you can successfully achieve that information? So you can see the situation is more or less analogous to the weak values, right? When you are having the weak values, if you want to access the higher amount of weak value, you need to compromise with the lower probability of successful post-selection. Here the case is similar, right? So if you want to gain the higher Fisher information, you have to have a cost, which is a lower probability. So we are defining a metrological efficiency, which is comprising of these two terms, right? And want to check what would be the situation when the information is actually higher. So after having all this, you can see this rho, this xi PS is just a notation for the metrological efficiency. So this part actually we can write it in terms of quasi-probability. This QMFK is the second part, is the Kirkwood-Dirac distribution, and the first part is nothing but there's a P theta AW square. So what is this K index for? K index for the post-selection block. Suppose you have 3-rank projectors, so the K would be 1, 2, 3, right? So N is like P theta AW square with the weak value as it is shown. So now you can see, if you write the efficiency in terms of probability and the Fisher information, you can express the whole post-selected quantum Fisher information in terms of this first part and the part which is consisting of this Kirkwood-Dirac quasi-probability distribution, right?
Let me ask you a question here. Can you go back to the previous slide?
This one.
So usually in the weak value case, you just have K is just one value of FK. Is that right?
Yes.
Yeah, and so here now you're allowing your projection is now a sum of projectors, and so you have to sum over these different K.
Exactly.
So that's the difference.
That's the difference. Yeah. Because otherwise, if you are having a single projector, means you can't have any choice of post selection, right? So this is why actually you need to have at least a projector which is rank greater or equals to 2, right? So this is why there's a K index is coming in. Yeah. So now I'm writing this. I'm writing this expression again because this expression seems a bit messy. So you don't have to remind anything. So this is the metrological efficiency is written again, and this is the form of Kirkwood-Dirac distribution. So now when I was introducing this Kirkwood-Dirac distribution, I have introduced a Wigner formula. So that Kirkwood-Dirac distribution can be written also in terms of this Wigner formula. So now what we are doing, this is the first term in the green box, is we are writing the similar expression for the system observable and the post-selection block, right? So now we want to check how we can harness the non-classicality that is arising from the system observable and the post-selection incompatibility. So now you can ask, why don't you go for the incompatibility for rho and AM or rho and FK? It might be another case, but here we are concentrating only at the level of the non-commutation between AM and FK, right? So far you can see the total expression, this total quasi-probability distribution is written like previously what I have shown. So surprisingly, what we see for pure states, everything what I'm dealing with pure states, there is no business of mixed state. So for pure state, this metrological efficiency is 0, right? When its KD distribution equals to the corresponding Wigner formula. Now what I have shown you, this Wigner formula, each element in Wigner formula are real, right? So when the Karpuk-Dirac distribution has a possibility to take complex eigenvalues, since it's a quasi-probability distribution. So now when you are insisting your Karpuk-Dirac quasi-probability distribution to have equality with the Wigner formula, then you can see there is no non-classical advantage. And this can be drawn from the commutation between AM and FK. And when you are putting this condition, your metrological efficiency becoming 0. So there is no non-classical advantage so far, right? So let me move on to the next part, right? So now you can see, so now we wanted to ask a question, when your Fisher information is going towards infinity, your probability cannot have that kind of unboundedness. So is there any bound in the metrological efficiency? So yes, there is a bound, and the bound is like less than equals to 4 multiplied by the system observable square operator norm. So here's the sketch of the proof, and the sketch of the proof is nothing but it concerns about optimization. So you can see the first part when I have written the metrological efficiency. So if I want to check when the condition, what would be the condition at which our metrological efficiency would be maximum, you can see the first part has to be maximum and the second part has to be 0, right? Second part has to be 0. So now this condition has already achieved when the second part can get 0, right? And you can see your metrological efficiency is actually bounded. Metrological efficiency is actually bounded by this term, this 4a square term. So after that, we will go on to constructing some information preserving post-selective metrological protocol. So I will not spending time into this. I will go to the main part of my talk. This is like how to construct generator, how to construct post-selection. You can see I have considered a second rank projector. This is why F1, F1, F2, F2. So this this is the initial state. This is the final state. And actually we are going to estimate the theta value. So these are all the protocols that I want to check whether this metrological efficiency and all the things we are describing, whether they are being preserved or not. So these are all the calculations, how to calculate the post-selected quantum Fisher information and the post-selection probability. Now see the last block. See the last block. So when you are having the last block, you can see the P theta Ps when this condition is being obeyed. It's like a cos square alpha. And the second part, which is actually the Fisher information part, is a 4 lambda square sec square alpha. And the last part, which is the metrological efficiency part, it's like a 4 lambda square, right? So now focus on the second term, the last box, second term. If you are having alpha value 0, if you see the construction, you can manipulate your alpha, right? If you put your alpha equals to 0 and alpha tending towards 0, your information is actually going towards infinity. On the contrary, what would be the case at the level of efficiency? You can see whatever be the case for Fisher information, the efficiency is always bounded. So what is this lambda square? Lambda square is nothing but the maximum and minimum eigenvalue difference. The protocol, the way I have constructed, if you see and you can check the difference between the eigenvalues, the maximum and minimum eigenvalues of the lambda square. So now I will come into the main part of my talk, right? So now, so far, actually, what I have shown you, when your Karpuk-Dirac quasi-probability distribution is positive, you can't have any metrological efficiency so far, right? So far what literature suggests, if you want to have any notion of non-classicality, you need to have the negative element at the level of your quasiprobability distribution, right? So we are actually exploiting the experimental setup that I have seen, that I have shown to you. So if you calculate the things, the first box, the KD distribution corresponding to the system, evolution, and post-selection. And if you see the second box, which is the right part of my slide, so you can check both of the, so it is very much obvious that the capital Q, the Wigner formula is a real. So each element would be real, right? So, and you can see the KD distribution part, even each element are real. But the difference is what? This KD distribution entries are not equals to the Wigner formula's entries, right? So if they would be equal, you know, and as I have shown you, and we have proved in our paper, that your metrological efficiency would be 0. But here the case is surprisingly different. The quasi-probability distribution and the Wigner formula are not matching. In spite of that, you are having the notion of non-classicality. How your notion of non-classicality manifested? You can see the first slide. In this experimental setup, your notion of non-classicality is manifested via your information is getting towards infinity. So our conclusion is positivity doesn't necessarily imply classicality. Rather, the condition that is more restricted, at least in terms of this protocol, that you have to satisfy this part, the small q and capital Q has to be equal. So here what is surprising is we have obtained the non-classical advantage only with the positive element of Karpov-Dirac quasi-probability distribution. And at least in this framework, you can see that negative element in quasi-probability distribution is not at all required to gain the advantage of gain the non-classical advantage. So far this is our prime conclusion, and this paper is an archive. You can check the archive link. So now I'm going to conclude my talk. So conclusion is how the Karpov-Dirac quasi-probability distribution is coming into the metrological setup, and how to harness this non-classical resource to get the advantages. So now let me say you all the Fisher information and all the things, whatever it is the post-selected Fisher information, whatever it is the classical Fisher information, those are all the statistical description, right? So you can't have you can't have a single trial. In order to have those bound, you need to have numerous number of trials. So what I have shown you, when I have shown you that we are overshooting the fundamental bound, that is actually at the level of single shot. Okay, so we are defining some positive quasi-probable distribution element, and we wanted to check whether at that positive element we can have some single shot advantages or not. So the conclusion is probably you can't have those advantages at the statistical level, but it is very much clear that the advantage is apparent at the single shot level. And the main conclusion and the main theme of the talk is this is not at all required to have a negative element in the probability distribution to have non-classical advantages. At least with respect to this protocol, you can say that you can have all the advantages with a positive element. And what we have argued, we have actually prescribed a different notion to determine the notion of non-classicality. This is not something that is bounded within defining whether you are having the negative element or not. This is something different. Then you have to check at the level of whether your Karpov-Dirac quasi-probability distribution is same as Wigner formula or something else. So this is more or less the conclusion. So now please ask me questions. Yeah.
Okay, thank you for the nice talk. I think I'll ask the first question. So yeah, so people are clapping. Thank you. People are saying, so appreciate that. I guess the first question I wanted to ask is, last week we had Nicole Younger-Halpern visiting us here at Chapman, and she is one of the co-authors on this other communications paper you mentioned. And as far as I understand, the main conclusion that she draws, and that with her co-authors, is also looking at this Kirkwood-Dirac function, is that they link metrological advantage to the negativity of the Kirkwood-Dirac. Now, what you're telling us is that, in fact, there are some cases where you can have a positive, complete positive quasi-distribution. Nevertheless, you get some kind of metrological advantage. So can you tell me, first of all, how your results either contradict or in some kind of concordance with their nature communication result?
Okay. So first of all, what Shetwright groups, what they did, so they first introduced the Kirkwood-Dirac quasi-probability distribution, and what they said, Kirkwood-Dirac quasi-probability, if you have an extended Kirkwood-Dirac quasi-probability distribution, this is the nomenclature that I am getting from their paper. So they are saying that at the level of extended Kirkwood-Dirac quasi-probability distribution, you have to have a negative element, right? So now our claim is, so the experimental protocol that we have shown, that is much more experimentally affordable, first thing. And the second thing is that means we achieve this whole advantage with respect to the positive element. And the main part of our conclusion is that how to achieve the non-classicality, means what would be the quantifier? What would be the quantifier that you can sense whether you are having non-classicality in your protocol or not? Yes, I agree. The Nature Communication paper by Shetwright and Nicole, so they argued from the perspective of Kirkwood-Dirac quasi-probability distribution and the extended Kirkwood-Dirac quasi-probability distribution. But our argument is something different. Our argument is how to catch those notion of non-classicality. Means if you are having the positive element, is it sufficient to have you are having non-classicality or something else? So this is why actually we are using the nomenclature of Wigner formula, and we want to check at the level of and we wanted to check everything at the level of metrological efficiency. So when they're sharing the same element, what would be happen at the level of metrological efficiency, and when there are difference, what would be happens? What would happen at the level of efficiency also? So more or less, actually targeting the problem in a different way. So they are claiming that you need to have a negative element at the level of extended Kirkwood-Dirac quasi-probability distribution. So we didn't go to extended Kirkwood-Dirac quasi-probability distribution. We ended only up to the standard Kirkwood-Dirac quasi-probability distribution. But our intention was to check means what would be the quantifier? What would be the quantifier? And means suppose if I am saying my system observable is A and my post-selection observable is F. So if I am saying there is some non-compatibility, suppose A and F are non-commuting, is it sufficient? Is it sufficient to have any non-classical advantages? So our article or our argument differs in that way actually. Yeah.
Okay, thank you. I think Lev Weidman has his hand up. So Lev, if you want to ask your question, go ahead.
Yeah.
Thank you for the talk, but I have to tell that I was somewhat lost.
Yeah, pardon. Your voice is breaking. Pardon.
What?
Yeah,
speak up, Lev. We can't hear you.
You cannot hear me?
Yeah. Now I can hear you. Now I can hear you.
Now it's better.
Now you can hear me?
Yeah.
Yes.
Okay. So it's all this very fancy concept, but if I understand, you have some parameter theta, and you want to find it, and you have some quantum probe which you put interaction with this system which has this theta,
right?
And then one method is just to look on this probe immediately Another method is just to make some post-selection, throw something away, and to look on what is left. Now, I don't believe that you don't say anything concrete, or maybe I didn't get it. What you exactly do after it, or what you're allowed to do after it. Clearly, after post-selection and throwing something out, the information that you have in your probe is less than it was before. You cannot get any advantage whatsoever.
Understand.
The only advantages in post-selection, which I know, and the weak value which is relevant for it, is when you perform particular type of experiment. And then if you look on particular experiment and you see that the shift is small, you cannot see it. You can enlarge it by making anomalous weak value. You have detectors which saturate, so then then you cannot use the whole data which come out, and you can use less data, but this data is much better, so you can get advantage. If you don't say anything concrete, how you take the information, I don't understand how you can get any advantage whatsoever.
Thank you for the question. So the answer is yes. So I will refer at this stage a paper by Todd Grun, though. So the exact name of the paper was like entanglement assisted weak value amplification.
Can you please go slightly slower?
Okay. So, at this stage, I would like to refer a paper. This is by Todd Grun. So this was about entanglement assisted weak value amplification. So what they did, they did some post-selection, and say they wanted to see, because in the business of post-selection, since you were discarding some data, so you were losing something. So now what they did, so they came to a particular framework of optimization where they wanted to optimize a maximum weak value with a lower PS, and they actually claim all the data you have, you can actually combine all the data at a particular basis with some correction term. So now I want to tell something more on this. The way we design our protocol. So the way we design our protocol, actually what we taken care of, that all the information in the discarded basis are 0, right? So what we have done,
but just say 0 is fine. So then you still don't get any advantage.
So no, the advantage I exactly agree. The advantage is not statistical. The advantage is at the level of single shot. So probably you can't realize that advantage at all.
Advantage what is the advantage?
What is the advantage means you are overshooting the fundamental limit at a particular trial.
What? Slowly.
Okay, sorry.
The
actually,
sound is not very good, so I cannot hear you clearly.
So the advantage is the overshooting the fundamental limit at a particular trial. Right?
You want to get information about theta, and you don't, let's say in the best case, there are really cases you make post-selection, and what it's thrown away has essentially 0, almost no information. But I still don't see any advantage. So how you get you don't get more.
Okay. So now you can see the advantage. So this is just see the last block. So the second part, that IQ theta.
All these things is kind of not the mathematics. I admit I don't understand exactly the mathematics, but you want to tell me that there is some information in your probe. Now you throw away, and now there is more information in your probe. This is what you want to tell me? I will not believe any mathematics that this can happen.
Okay. So I completely agree with you. So means our initial concern was to quantify means why this means why this violation of fundamental limit, even at the particular level, even at a single child, is happening. So this is why actually we wanted to check what is happening at the level of quasi-probability distribution. So we thought there might be something because of this quasi-probability distribution, some way or what, actually they are having some weak value amplification kind of thing. Okay, so since everything that is encoded in the post-selected quantum feature information is more or less in a form of weak value, so we thought this might be a case of weak value amplification at some particular level. So this is why we trialed out. And actually our main concern was to see whether this advantage can be attained without the negative values. So I agree completely with you. This advantage cannot be realized statistically. But the advantage actually we are seeing, this is at a particular trial and some particular value of the quasi-probable elements.
Hey, Subhrajit, let me try to translate and re-express what you're saying in a different way and see if Lev can understand this, and if you agree. So if you look at your formula, the bottom line, the squiggle variable, C, that's your fundamental limit. That's your maximum Fisher information of the entire
I don't care about Fisher information. I want information.
Listen, Lev. Just be quiet for a minute.
Is not very good. Way to find information. There are many problems with information. This is
okay.
If I want information and I don't say how I measure, there is information there. It's clear. It's not Fisher information. If I will make Fisher information big, but I don't know, it's not what I need. Who cares?
All right. So what I'm saying is that your post-selection probability is like cosine squared. Your post-selected information is 4 lambda squared secant squared. And so if you multiply them, that'll change your fundamental limit. Is that right?
Right. Yes.
So what Subhrajit is saying is that don't take a bunch of trials. Just take one trial and maybe you get lucky and you get a lot of information in just a single trial. Is this what you're talking about?
Yes, because yes, you can see, and the one thing, yes, means if you see when you are setting alpha equals to 0, suppose you are setting alpha equals to 0, this IQ is going beyond some fundamental limit, is going towards infinity. And if you check this P theta PS, I'm saying wrong. This alpha equals to 0, it has to be like alpha equals to pi by 2.
Yeah, pi over 2. Yeah, that's
alpha
right.
Equals to pi over 2. So now you can see, so in order to have the advantage, what you have to combat with, almost zero success probability. That's how this total thing is consistent. This is not like you are getting this infinite information with some finite probability. Your probability is 0. So you might be probably you might not be as lucky to have the information, but if you can touch those lines, probably you can have. So this is what I wanted to convey. Yeah.
Okay, thank you. Tathagat, you have a question.
Yeah, nice talk. So I had kind of 2 questions. So first is a follow-up on what Professor Jordan asked. So if I understood your explanation correctly, you were saying something along the lines of this protocol it presented being more affordable than the ones that are presented in Nicole Younger Halpon's paper.
Right.
So could you expound on that, because they apparently did the experiment, like the related experiment.
Okay. So the protocol is advantageous in terms of so we didn't experiment it. So the advantage in terms of what they did at the level of the total experimentation had 4 levels. So we had completed the procedure up to 3 levels, and so means we have removed the degeneracy of the theories, right? So you can see all the eigenvalues everything is non-degenerate, right? So these are the restrictions that we have removed. So what they explained for 4-level system, and the theory was degenerate. So we have explained for 3-level system, and it's completely non-degenerate. Yeah. in that respect, it is helpful. But so far, actually, it would be true to say I don't know. Means with losing this, with relaxing this condition, whether it would help us in attaining some, in reducing some experimental cost or not. So yeah. So at the level of this reducing this energy levels and lifting the degeneracy, we are saying that our protocol is much affordable, at least in terms of design.
Okay, thank you. And one more question I have is, when you introduce that quantum Kramer-Rao bound, you basically showed mathematically that if the post-selection probability goes to 0, you will be able to basically get past the classical bound, the bound provided by the quantum Fisher information physically. So I'm wondering, how would you make sure that the post-selection probability goes to 0?
No. Post-selection probability. Okay. So whatever you see, when I was talking about this Karpov-Dirac quasiprobability distribution, so I have shown you a similar notion of weak values that is already encoded in the Karpov-Dirac quasiprobability distribution, right? So now, if you think of in terms of weak value, when you are having higher weak values, you need to have lower successful post-selection probability, right? So there is a trade-off. So if you want to have higher weak values, you need to combat with lower post-selection, lower amount of successful post-selection. So this is how actually we are resembling the thing. So if you want to have, or if you are having infinite amount of Fisher information, post-selected quantum Fisher information, you will have, you will very rarely have the access to that, because the successful post-selection will be less. So this can be very much understandable from our paper. So I forgot to mention the expression that was written exactly in terms of weak values, right? So this is more or less the scenario. This is how this weak value and the post-selection metrologies are kind of having some similar pictures.
Okay, I have another. Yeah, good. I have another question. So usually in the weak value metrology, you involve a system and a meter, and you look at post-selection on the system, and you see then how the meter shifts conditionally on that. Right. Whereas here, it seems that there's no meter, and it's the same. And the same is true in Nicole and Seth Lloyd's paper. Right. They just have some kind of generalized measurement on the system, and then they post-select again on the system. Do I understand correctly?
Yeah. Yes. So yes. Exactly. So means we are so far not having this weak measurement kind of setup, but still we are enjoying the weak value kind of thing. So this is coming completely from this notion. So I should show you this expression probably. Probably this. Okay, let me go to this. Yeah. So it's like a means when you are having a state, and now first you are measuring AM, right? So after measuring AM, you are having some pull-up state, which is rho prime, right? So, and you are having some outcome AM. So now, conditioned on that outcome, you want to measure once more for the observable BN. This is kind of sets a scenario of weak value type, right? So I will show you this thing. Now you can see the second line after the green box and the right hand side. It's like AM is the projector for the observable, and the BN is the projector for the second observable. So this is how they are setting the pre-selection and the post-selection type thing. So this is how the notion of weak value is coming in.
I think this is why you need the fact that the post-selection is not just a single projector, but it has to be at least a sum of projectors.
Exactly.
Because you have to get some kind of interference going.
Right. Because so I forgot to mention actually a beautiful expression that I have described in our paper. So this is like Fisher information. Post-selected Fisher information is like AW1 minus AW2. So what is the AW1 and AW2 is? A is the system observable. So the weak value at the first post-selection basis and the weak value at the second post-selection basis. Now, if you are having a single line projector, this AW1 and AW2 are equals. So you can't have any information at that level. So sorry, I forgot to mention that would be much more transparent if you look at that expression. Yeah.
Okay, thank you. Any other questions from our audience?
So I have a question. It would be a bit follow-up on Professor Weidmann's question. Could you please come back to the slide where you discard of some states and keep some of them?
This one?
Yeah, exactly. Like it really feels extremely unintuitive that you can gain any advantage despite the fact that it discards certain set of states that has in principle information about the parameter encoded in it. So could you, in simple terms, explain to me, like, under what circumstances would I want to realize this particular type of protocol, and what advantage would I gain? And
in terms of post-selection, you were talking about.
So could you, for example, provide me an example of physical system for which I can realize this type of protocol and gain some advantage?
Physical system, suppose, okay. So suppose you are having a state, so now you want to pass it through a block where there is a magnetic field, right? So because of that magnetic field, your state will get some shifting. So now, after having all those arrangements, so you want to measure what would be the strength of the magnetic field is, or how much your state got shifted because of that magnetic field. Suppose these are all the unknown parameters that you want to describe, or that you want to estimate. So, and keep it in mind, the procedure that we are asking for, in order to have this kind of metrological protocol, you need to have pure states, and the encoding procedure, which is going on in the yellow block, it has to be like a unitary encoding. Okay, so this two restriction has to be maintained. So after that, you need to have some post-selection. So post-selection means, suppose you have 3 orthogonal bases where you want to post-select your state. So since you are having 3 different bases, all the information that you are having, for the time being, we are saying that it's a closed system. So all the information that your state is actually having, that will be shared in between 3 bases. So we designed our particular protocol in that way so that failed post-selection won't have any information. Or if there is some information, that will be very much less. So now, in order to have this kind of scenario, you need to configure at what kind of optimization setup you will have this. So now it will require whether you want to have maximized weak value or the maximized post-selection. So whatever we have done to make the things to have the weak value maximum. So this is more or less the setup. So yeah, so if you see this calculation, I would rather suggest you to see this calculation. If you see this calculation, if you check the information at some information is only contained in a particular basis. So there is no information in the discarded basis. So there is no afraid of having that you might have lost some information. So more or less all the information that the state is carrying, we are kind of keeping the information intact, so that if there is a possibility, you can have some advantage. So this is more or less the case. So I can't give you exact experimental setup, but this is more or less the scenario. So how to estimate some unknown parameters and what would be the strategies. Yeah.
Okay, I think Justin has a question. Justin, can you come on and unmute and ask your question?
Yeah.
Sure. So I came a little bit late, so I apologize if this question's off the mark. But it doesn't seem to me like you're saying anything terribly different from the paper I linked in the chat. So I was curious if you happen to know this paper, what you're talking about compares to the analysis in that paper, and then what's new in your analysis.
Yeah. It's a new.
Oh, good. Actually, he actually referenced this paper earlier in the talk. Just
Yeah.
Oh,
So
very good. I was just not here for that
So
part.
this is the paper. Yeah. Right. So this is the paper. Okay. So what we wanted to have, the new thing is how to define the notion of non-classicality. Because when you are using this quasiprobability distribution, so we are actually setting a reference point in terms of Wigner formula. Okay. So now there might be a protocol that you can enjoy the non-classical advantage even without having the negative elements. So now we are saying you can have different many situations, right? So we are restricted only up to the situation when you are having the non-compatibility in between system observable and the post-selection observable. So now you can also have the non-compatibility between your state and a particular observable, the state and the post-selection. So now at this particular level, what would be the quantifier to say that you can have a finite metrological advantage? Okay, and so I forgot to write up some of our expression that we have expressed in our paper, and more or less actually what we have done new in this context, we have prescribed some geometrical interpretation in terms of Bergman invariant. So how to have the situation of optimization and what would be the case in terms of geometric phase. So that I have not included in the paper. So mostly my concern was to see, or the claim was like, does positivity always imply classicality? So this was our main concern. And through this example, actually we are breaking the statement. Yes, the positivity doesn't always imply classicality. So this is more or less our conclusion. So there are several many parts that we have deduced in our paper, so that I have not included because I wanted to be the talk to be coherent. So that's why I discarded this part. Yeah.
okay. Thank you. All right. Any other final thoughts? All right. If not, let's thank Subhrajit very much for this nice talk. So thank you for that. Yes. People are applauding virtually. So thanks very much again, and we'll sign off now.
Yeah, sure. Thank you.
Bye.
Bye. Thank you.